Good morning, ladies and gentlemen. My name is Filip Zemajtis. I'm a PhD student at the University of Wisconsin-Milwaukee. The topic of my today's presentation is superhydrophobic, ice-phobic, and photocatalytic coatings for concrete. The work was done under the guidance of Dr. Konstantin Sobolev. So first of all, it will be important to introduce some important for this presentation definitions. So the photocatalytic reaction is a chemical reaction that is driven forward by exposure to light. Because of the formation of radicals that are capable of decomposing bioorganic material as well as some inorganic material like nitrogen oxides, we can obtain some self-cleaning and decomposition of those materials. So hydrophobicity is the property of the material that repels water, and because of this, when the water is dropped at the surface, the contact angle from 0 to 180 is created, and the hydrophobicity is the contact angles between 90 and 120 degrees. So this is, for example, situation with concrete that is modified hydrophobically with some polymethyl hydrogenated siloxane. Standard concrete is considered a hydrophilic surface where contact angle is less than 30. When we speak about the over hydrophobic surface, where the contact angles are 120 to 150 degrees, we need to add to our hydrophobic emulsion solution whatsoever some micro or nanoparticles. In order to enhance this state, to obtain super hydrophobic surfaces, we will have more than 150 degrees of contact angle, and our concrete will need to be modified with micro and nanoparticles. And we can see this, the presentation of the lotus leaf, the schematic of lotus leaf on the right, in here, where we have the epidermal cell microstructures which are coated with wax crystals, and this corresponds to superhydrophobic surfaces. And the water is able to roll off the surface without wetting it, and in the same time, it's taking all the debris with itself, so it's self-cleaning property. So moving forward, I would like to answer the question why we care about about protecting the surface of the concrete. And this is because, okay, going back. In this situation, we tested 10 different compositions of concrete. Those concretes were not protected. Those concrete were evaluated to have the freeze-thaw performance and durability factor of more than 92%. And the surface resistivity corresponds to the concretes with very low permeability. The differences between the coatings are the plasticizers used. The letter M in the table there stands for mid-range water reducers. H stands for high-range water reducers. So all the even-numbered samples were using the high-range water reducers. All the odd-number samples, mid-range water reducers. And the Portland cement was replaced in some percentages with supplementary cementitious materials like fly ash class C, fly ash class F. And salt scaling test was performed, and after 50 cycles, we can see the surface of the concrete is deteriorated pretty significantly. In some situations, we had the weight loss after those 50 cycles more than 1%, which is really bad. Even though the concrete is considered of good quality because it passed the durability tests, it has very low permeability, we still need to protect the surface of the concrete because there are deterioration happening there. And 50 cycles, for example, corresponds to the one season in Wisconsin where I came from. So only after 1 year, the concrete surface, unprotected concrete surface may look like this. So now I would like to present some coating envisioning, so how we envision the process of application and what we would like to obtain. So we propose two approaches. One will be the single layer, where we will apply only the second layer of interpenetrating zero VOC hydrogen siloxane emulsion on the surface. And the second approach, which is double layer, where we will create with some inorganic polymer or inorganic ceramic on the surface, the hierarchical roughness, which will be able to enhance the contact angles, more or less mimicking the lotus leaf, which we can see as well on this micrographs on the right. This is the surface of the lotus leaf, which is considered very, very predecessor of hydrophobicity and self-cleaning properties from the nature. And we can see the surface the micro pillars formed from the wax. which are roughly 10 microns in dimension, which are coated with additional nanocrystals. And because of this, corresponding contact angles are the water droplet is very hydrophobic. Moving forward, I would like to present now a few slides about the single layer approach. So in this situation, we coated, as I already mentioned, the hydrophobic emulsion containing the nano or submicron particles inside the composition. So those two different schematics differs from themselves with the PVA fibers present in the state on the right side of you. So we have the concrete, which has polyvinyl alcohol fibers protruding from the surface, and this creates this additional texture, this additional pattern on the surface that allows these particles from the formulation to create better, higher hydrophobic states. So we can see that the particles are distance between themselves around 50 microns, and both situations create good hydrophobic angles like over hydrophobic and super hydrophobic. So moving forward, this slide presents you some typically used hydrophobic materials. Some of those materials are typically used by DOTs to coat the concrete and protect the concrete surface. And here I presented the comparison of contact angles of those materials with UWM developed mixtures, which we can see that at UWM we were able to obtain over hydrophobic and super hydrophobic states. This micrograph shows you the concrete structure, concrete surface that was coated or uncoated. So at the first one, we have the reference concrete. The goniometer was used to obtain the water droplet angles. And we can see that reference, as everyone here know, that is very hydrophilic surface. So we can see the contact angle is less than 30, and the droplet is wetting the surface. The differences between MK1, MK2, and MK3 is that for MK1 situation, simple, we don't have any nanoparticles embedded into the hydrophobic emulsion. In this situation, we were able to change the surface properties from hydrophilic to hydrophobic. So it's good. We want to have it hydrophobic. However, we want more. Difference between MK2 and MK3 is that we have the nanoparticles added at different stages at different times of emulsification process. One situation, MK3, get us the core structure where we have nanoparticles embedded into the hydrophobic bubble, the hydrophobic oil bubble, which is like more or less 2 to 10 microns in dimension. And this situation does not add anything valuable in terms of contact angle behavior at the surface. However, when you consider MK2, the shell situation, where we have nanoparticles added at the last stage of emulsification, we have formation of shell around the hydrophobic bubble, and this creates the higher surface area and higher contact angle because of this, because it corresponds more closely to lotus leaf scenario. On the right chart, we tested as well. We would like to evaluate if application of two coats of the same formulation will change the surface contact angle significantly. And only in the situation MK2, where we're considering the shell one, we have the increase of contact angle. In other situation, the increase was not significant, or it does not increase at all. So now this is the small slide about the double layer approach, our newest composition, where we would like to add additional layer with hierarchical structure made of the ceramic, inorganic ceramic, that will impose the texture proper for obtaining super hydrophobic angles. And this is a small block diagram that shows the pathway of the experiments. And what I want to emphasize in here is just those characterization spots. So at the very beginning, when we had the solution stage, we characterize the solution if it is suitable for further application, if it possesses some photocatalytic properties, if the particle size distribution is correct, if it is just suitable for application, and if we will obtain the proper properties at the end. So this block diagram chart was done for metal substrates because we were using different substrates, not only concrete. However, it's applicable for various different materials. After substrate was prepared, application, spin coating, spray coating, sintering, 1 hour, 250 degrees Celsius, another characterization. Then this was characterization of ceramic, where we have only one layer that is very hydrophilic. And then we apply hydrophobic agent with spraying, and it was conditioned at room temperature and then characterized. So moving forward, this is a texture that we obtain of this ceramic layer, and we were able to impose the crystal structure at the surface that was spaced between themselves. And the crystal size, as you can see in here, is more or less 10 to 15 microns, which corresponds to the micrograph that I presented you at the very beginning of this presentation of the lotus leaf. So we have this lotus leaf-like structure. Of course, it does not look the same, but it creates the same, it serves the same role. We as well tested the coefficient of friction in terms of roughness, because we heard that that some people are concerned that when hydrophobic coating will be applied, it will impose some dangers for pedestrians, for walking, for driving on the surfaces. So we tested the coefficient, how coefficient of friction changed. We had our uncoated specimen. And this test was done for ceramic, so it has that kind of roughness, and it created our benchmark, or what to expect from the base material. When we created some samples that was hydrophobically treated, so more or less this situation, we have increase in coefficient of friction, which we expect. And when we coat it with hydrophobic solution, emulsion, we have a drop. However, this drop is not significantly below the benchmark that we established with uncoated specimen. Moving forward, this is the test of imaging with cold neutrons that was performed at Polscher Institute in Switzerland at ICON facility. And what we were trying to do in here was to evaluate if the coating in here, the coating layer was 70 microns, in penetrating to 70 microns, was keeping the water off the surface, or this water will be going into the surface or not. So we were able to use the Beer-Lambert law principles of attenuation of neutrons. So the sample is positioned like this, the coating is here, we'll see looking like this. So imagine X-ray diffraction, but with neutrons, not X-rays. This is the same picture. We are bombarding the sample, which was the ceramic sample, 9 by 9 by 9 millimeters in dimension. So this is the sample, 9 by 9 by 9. And we were able to see what was the coating thickness. The layer is uniform, water droplet contact angles over hydrophobic to super hydrophobic, no water going into. How this pictures was created, we subtract the dry image from the situation at the very beginning without any droplet, from the images of dynamic images when the droplet were coming, when we were sitting the droplet and waiting what will happen. And we can see that here is like no surface whatsoever. However, it is there and it's visible in here. Those are the same picture, but after the processing. So we had any penetration of water through the coating or to the coating whatsoever. I as well created a test, performed a test. I scratched manually the sample so the flow was visible, and I check it if it changed anything, and it does not change anything a bit. So this is very good. That will help us to obtain some proper features. Moving forward, on this, this is the output of the goniometer. We can see the droplets placed at the surface in the situation, one layer scenario again. This is concrete surface, fiber reinforced concrete. We can see contact angles very that are high, and the water is rolling off the surface after some time without wetting it. The same sample was tested for ice rebound at minus 15 degrees Celsius, so it's 5 Fahrenheit temperature in freezing room. So the water was dropped at the surface. This is water, the grayish one. This one is salty water, freezing point much lower. That's why rebound is less, because it does not freeze that fast. Super fast camera was used to obtain it. So we obtained the outcome that the ice is not accumulating at the surface. It's not attaching to it, and the water, even icy water, is not there. Situation, real life situation application. This is the entrance to the parking lot at UWM. This area was coated hydrophobically, and as we can see, it's rainy day. The concrete surface looks, as all concrete surfaces, it's wetted, it's wet, and this is the area where we have our formulation is not wetted. in this situation. This this picture was taken after 3 years of service life. So now it is 5 years, more or less, and we see some wear off. So we can hypothesize that 3 years is the lifespan of this coating at regular non-fiber reinforced concrete, because as we know, not all concrete is fiber reinforced. Returning back to the characterization of the solution, I mentioned at the very beginning that we will be going back, that we would like to obtain some evaluation if the sample is good, if the formulation is good. So why methylene blue is good for evaluating the photocatalytic properties? It's because it's organic dye, and because of the radical formation, it's decomposed to colorless structures, which is visible in here. The test was done, we irradiated with UVC light for different increments of time, and the reference and 0 minutes is the same sample. One was centrifuged for the purpose of the UV-Vis test, which will be performed later. We can see 0 minutes, the sample is pretty bluish. After 30, we are decreasing, we are losing some color, and after 90 minutes, we don't have any methylene blue present in the formulation whatsoever. It is as well important to mention that 663 nanometers is a maximum characteristic wavelength for methylene blue, and it's presented in here. The bigger the drop will be at this UV-Vis outcome, the more methylene blue we have in the in the formulation. So in the reference situation, we have big drip. In the 30 minutes, lower. At 90 we have no drop whatsoever. This is artifact in here that should not be considered at all the same wavelengths. This slide, I will already play the video. This is the same sample that was tested for photocatalytic decomposition. This is our setup, the NOx analyzer, nitrogen gas, the chamber. The sample was coated with our formulation, with a two layers of formulation, and we have a very good hydrophobic response into this under the turbulent flow from the top. We have some outcome of this NOx analyzer. We have the NO conversion, nitrogen oxide conversion of up to 75%, which is decreasing with the concentration of nitrogen oxide. But however, in the same time, rate of NO abatement is increasing pretty constantly with NO concentration. Moving forward, these coatings can have additional features like antimicrobial, for example. So this situation was tested, and the specimens were submerged into the gel, which was the perfect environment for the bacteria to grow. They were incubated for overnight, and at the very beginning of the incubation, UVC was flashed at the surfaces for an hour. As an outcome, we have a reference uncoated situation where we have those bubbles here. Those are colonies of E. coli. And here, coated situation, we don't have any bacteria present. So we can say that bye-bye E. coli in this situation. As a conclusion, as already mentioned, we can hinder the water transport because the water is not penetrating into the surface. We don't have tendency of ice accretion. This is kind of hypothesized conclusion because we did not perform any corrosion tests so far. However, because the water will not penetrate into the surface, we will not have the corrosion of reinforcement because of this problem, and we will not have the loss of structural integrity because of the expansion and other stuff. And photocatalytic reactivity can assure us self-cleaning improvement of air. And what is as well important, as you all know, now it's very good time to talk about the CO2 gases. If we increase the durability life of our structure because of coating the concrete with those formulations, we don't need to redo the structure again and again. So the reduction of CO2 emission will be there. And I would like to acknowledge all the companies that helps with this research, without whom this research will not be possible, as well as the members of our extended UWM team. If you have any questions, if we have time, I would be happy to answer. If not, I will be in the room to chat. If not, please send me email or Dr. Sobolev. And of course, thank you to my wife.